This is Bo Yang. I'm from Tencent Games Digital Content Technology Center. Today, I'll give a talk about 3D reconstruction for game development. Here is the outline of my talk. First, I'll discuss about commonly used methods for 3D representations. Second, I'll talk about one important unsupervised learning method for 3D reconstruction. That is differentiable rendering. Third, I will talk specifically for 3D game character reconstruction. Okay, let's see first, 3D representations. There are many ways to represent 3D objects, so I will talk them one by one. First, mesh. This is the most commonly used way to represent a 3D object. It is widely used in most industrial tools, and for example, in games, in movies, lots of these things. And it is easy to add constraints. However, mesh has some limitations. For example, it is difficult to change the topology, and usually it has complicated data structure. So another way to represent 3D object, it is voxel. So voxel, I consider it is comparable with pixels in 2D. So voxel, it is just like 3D cubes in 3D space. So it has a very flexible topologies, and it has regular structure for each component and easy for computation. For example, convolutional neural networks, because it is very regularized, so it is very easy for computations. However, voxel has its drawbacks. Because voxel need to fill the space, each of the space cells with one specific small voxel element. So it has very high memory cost. And also, if we want to have very high resolutions, we need to have much more higher space cost. So it usually has a limited resolution. The third representation method, it is point cloud. Point cloud, it is just using the points in the 3D space around the surface of the object, so that it is very easy to represent any kinds of objects without any limitations. It is very commonly used in many applications. For example, in the autonomous drivings or in the 3D understanding tasks, we don't really need to build the 3D objects. Using the point cloud, we can already understand what is happening, what are these objects. It is very easy to control. However, its drawbacks are the following. First, it has very irregular shapes. The points are not evenly distributed in the 3D space. Some parts we have points, some parts we don't have. So it is very difficult to add constraints because the points are almost arbitrary. Another way, it is the combination of parametric models. For example, this chair, it is combined of the 6 parts. Each part, it is a regularized object. So we can see that the benefit is that we can use very small memory cost to represent a very big object, because each part, we just need a few, very few parameters to represent. However, its drawbacks is very obvious. Not every object can be easily to decomposed into these parametric models parts. So it can be only applied to very limited, simple objects. Next, depth map. So depth map, it is another way. Usually, depth map, it is not a fully representation of the 3D object, because depth map always consider only the view angles from the current cameras. So we can see, we can measure the distance from an object to the camera center, but we can't see what is behind the object. So only one view angles of the object is clear. So the benefit is very low memory cost, because it uses 2D depth map to represent the object, and it is very easy and quickly for computation. However, as I said, this is not the true 3D representation. It is only 2.5D. So the sixth way, it is called implicit representations, and it attracts many attentions in recent years. So implicit representations does not assume any predefined shapes or any constraints of the objects. It is just using an implicit function to represent the surface of an object. For example, for any points outside the object, it is considered that the function will give greater than 0 values. And for the inner part, it is smaller than 0 value. So on the boundary, it is 0. So that based on this implicit function, we can see where it is of the boundary of the object. So its benefits is compatible with any topologies. And it is theoretically infinite resolutions because the implicit representations, the function, it is a continuous function across the whole space. But its drawback is it is difficult for rendering, and also it is difficult to add constraints. So because today's talk, it is mainly about the games industry. So here, let me show what models games needed. So in the game industry, Mesh, it is a standard format for productions. And topologies may vary significantly, even for the same game type of object. For example, for humans, here it is a model example from the QQ Speed game. So we can see that although it is a regular human shape, but the clothes could be very complicated. So it requires very high accuracy. For example, we can see many details in the clothes. In the game industry, we need to reconstruct these details. Otherwise, it is not very pleasing, and the users will not be satisfied. So the models usually have very high complexity. Okay, what is our strategy? Considering the requirements in game industry, so we plan to use the implicit surface representation because it is very suitable for high accuracy requirement. In terms of the mesh constructions, we use the Marching Cube algorithm to convert the implicit field to the mesh. This has already been a standard method for several years. Okay, now let's talk about the second part, differentiable rendering. So the differential rendering tasks, I will talk about two major works from our team members. So one, it is soft res. Another, it is the implicit surface differentiable rendering. So the first part, it is a DR for the mesh part. The second, it is the DR for implicit surface. I will talk them one by one. First, let's see why we need differentiable rendering. So what is a rendering? Rendering requires we have a 3D geometry, we have texture map, we have materials, lighting. All these parts together, we get what the object will be looking like in this condition. So we render this 2D image to make it as true as possible. So what is the rendering doing? It is building the bridge from the 3D graphics to the 2D visuals. What is the differentiable rendering doing? It is doing the reverse problem. So it is from the 2D images that we can infer the 3D informations and also make the rendering process differentiable so that we can backpropagate the 3D geometries. So here let me say it again. Differential rendering enables the direct optimization of the 3D properties based on image-based supervision. Gradients flowing from the image pixels to the 3D directly. So, what are the applications? It has many useful applications. For example, the pose estimation, 3D reconstruction, material inference, and lighting estimations. As long as we have enough 2D information, so we can estimate all these 3D properties. So one important part I want to emphasize, all these parts are unsupervised. Okay, now let's see what is the DR for meshes. So first, software as it is already open source. So code is available on the GitHub. So, and also it is adopted by the PyTorch 3D as a core algorithm for differential rendering. So if you like this algorithm, you can already use it on PyTorch. So first, why we need differential rendering? Because standard graphics rendering is not differentiable. Why? First, let's see what are the standard rendering tasks is doing. Let's see, we have some 3D vertex. So during the rendering task, one important step it is called rasterizations. We need to convert these vertex into the 2D spaces and quantize them. So we see that this is the frame buffer. From the original part to this one, these steps, it requires the discrete sampling. But this step is not differentiable. The second part, it is called z-buffering. So what is z-buffering doing? Suppose we have a camera viewing angle from along the z-axis. So we see that the orange object, it is ahead of the blue object. So for the overlapping part, we can only see the part from the orange object, but not from the blue object. So this requiring that we need to ordering the depths of the objects along the camera axis. So this is called z-buffering. This step is also not differentiable. So here, let me talk about some previous works. So these are the two mostly related works. One is OpenDR, another is called Neural 3D Mesh Renderer. I will not go to details of these algorithms, but both directly use the OpenGL in the forward rendering, and they approximate the rendering gradient using the handcrafted functions. What's the problem? So these methods will have the inconsistency between the gradient during the backpropagation and the forward rendering. So this will lead to very serious problems. So what are our works doing? So first, let's talk about the rasterization part. How do we make the rasterization differentiable? Here it is a rendering pipeline. For the rasterization, we see that inside the triangle, let's say there is a face called Fj. So the traditional rasterization inside F, it is blue. Outside F, let's say it's red. So there will be a suddenly change of the color across the edge of the boundaries. So this makes these steps undifferentiable. So this will cause zero gradient in almost every part. So how do we make this step differentiable? Here we use the probability computations instead of the pure rasterization algorithms. For example, here we have a triangle. We have a point P. So here the label of the P, it is not just a binary switch from the inside to the outside, but it is a probability according to its distance to the edge of the surface. So that we will make a probability distribution in the whole space like this shape. The higher the possibility is, it is more likely to be inside the triangle. Otherwise, it will be outside of the triangles. So, after using these soft rasterizations, we can make this as a differentiable steps. So how do we make the distributions change? So we use a sigmoid function, so that inside, outside, and at the borders. So every point would be differentiable. We have gradients everywhere. Okay, now let's talk about the z-buffering. Traditional z-buffering, it is like this. We have point pi. Okay, let's using an axis towards the cameras. Okay, there are many surfaces that have intersections with this point, but only the first one, it is has the contribution to the point P. So because it is one hot voting, so it is not differentiable. How do we make the z-buffering process as a differentiable step? We make the traditional z-buffering also act as a soft z-buffering. So the final color of a pixel, let's say pi, it is a probabilistic aggregation of all possible triangles along the z-depth directions, depending on their relative depths. How do we do that? So here, it is the aggregation function. We can see that the final pixel, it is the weighted sum of all these triangles' appearance. And the weights, it is based on their relative depths. So the closer the triangle is to the pixels, it has a higher weights, so that its contribution to the pixel appearance will be higher than the further triangle pixels. So what's the benefits? Because of such probabilistic aggregations, we have the gradients from the point pi to every part, not only to the one triangle, but to all triangles. Let's compare our differentiable rendering with two previous works. So here we can see that we have the gradient from pixels to the triangles. However, during the OpenDR, only these parts, we have the gradients. For other parts, we don't have any gradients. And for the NMR, so we have gradients to Y on these two blocks, gradient to X on these two green blocks, only the pink ones that we have gradients for both. However, for our method, we have gradients everywhere. So here it is an example of what's the effect of different parameters. So actually, these parameters, gamma, it is defined. So we can see that when the gamma is increasing, so it becomes more and more transparent. So what does that mean? So the z-buffering steps, so the further layers will have higher gradients to move backwards. And another parameter, it is sigma. So sigma, it is for the rasterizations. Because for the rasterizations, we use the sigmoid functions. So with bigger sigmas, so the edge of a triangle becomes more and more blurry, so that we can see that different combinations can have different these kind of results. So here are some differentiable rendering reconstruction results. So we can see that by setting different parameters, we can have quite different results. Here it is applications for the single view mesh reconstruction. So we can see that compared with another 3D unsupervised method, NMR, our reconstruction results is much more accurate than that one. For example, the very thin hole for the light, and also the structures of these chairs, guns, cars. So we can already reconstruct very smooth and also reasonable results. Compared with the pixel to mesh method, our results are still comparable. But remember, pixel to mesh, it is a supervised learning method. However, our software, it is unsupervised. Here are more results. This is for the color reconstructions. So we can see that our approach can still learn very solid color palettes. And this is a quantitative comparison with state-of-the-art. We can see that our reconstruction performance is better than the previous methods. Here it is applications for shape deformation. So we just deform a regular shape, for example, just a ball, and to deform it according to the target image. We can see that using the same ball, we can deform it to car, to airplanes, and with very accurate details. Okay, now let's talk about differentiable rendering for the implicit surface. Okay, what is an implicit surface? Here it is a unit sphere. How do we define it? We know this function is a very accurate representation of the unit sphere. This sphere divides the 3D space into two parts, outside and inside. Between the boundaries of the outside points and inside points, it is a sphere. Okay, here comes a more complicated object. We can't find an easy function to represent it, but we can still find an implicit function to define this complicated object. We divide the 3D space points into different parts, outside and inside. So the boundary between the outside and inside becomes the surface of the object. How do we find it? We can use the Marching cube algorithms to convert the implicit field into a mesh. Let's see the conventional techniques. How do we rendering the implicit surface? So this is a rematching method. So we have a point, we have a ray. So we check the steps, and until we find the change of the sign. So we know that there may be an intersections. And after that, we use the binary search to find where it is the surface. But here, there may be some problems because we need to carefully select the steps. If it's too big, for example here, it may miss the intersections. We will consider, okay, this ray does not intersect with the sphere. So this will cause some error. So here, it is a sphere tracing method. What this method is doing, it is use a circle for the point A, and what's the radius? Radius, it is until the circle, it is intersect with the surface. Okay, now we come from this ray directions, and we just move the point from A to the new point on the sphere. We continue such steps until we find a close enough point to the surface itself. So this is a more safe way to find the surface. However, it is very time consuming, and more important, it is non-differentiable. Okay, let's see how do we make it differentiable. Here we have some distributed 3D anchor points, and we build the occupancy field evaluations for each of them. Each of them, it is a sphere, but here in the 2D, we just use circles. So the deeper blue means that the probability it is higher. And each anchor point has a spherical supporting region for computing the ray anchor intersections. Let's say the ray is coming from the bottom to top. And here, we perform the recasting with boundary-aware assessment. The assignment, it is from which point, which silhouette that we intersect with these spheres. And we aggregate the intersected anchors along these rays. And we compare it with the ground truth, so that such laws will help us to make the back propagations. Remember, this is similar with what we already done that in the differentiable rendering for the mesh. So idea is similar that we convert the binary part into a probability aggregations. So here it is a pipeline of the unsupervised learning for implicit surfaces. Here we give a shape. We have some image encoders by using neural networks and give a 3D sampling point P. We concatenate it with the encoder and we pass it into a decoder. The decoder will give a probability of the point P to show whether it is outside the object or it is inside the object. So by calculating many points, sampling points P in the 3D space, so we can finally get the surface of the object. So the loss function has two parts. One, it is the silhouette part. Silhouette means that whether the for each point P, that its estimation is correct. Another is a geometric constraint. Geometric constraint means that for the neighboring points, their normal should be similar. And so that by adding such constraint, so we try to reduce the sudden change of the labels in the 3D space so that the reconstructed shape will be more stable. Here are some results. So we compare our method with some previous methods, also together with our soft REST approach. We can see that our soft REST approach already much more accurate than the previous ones, but it still has obvious limitations. For example, for the airplane, there is a hole inside it, but our soft REST can't construct the hole. Why? Because soft REST, it is deforming an existing mesh. It can't change the topologies. However, our new method, we can reconstruct these details more accurately. Because the implicit field, has no prior constraints of the topologies. The implicit surface can be any shape without any constraints. Here are some quantitative evaluations. We can see that our IOUs are much higher than the previous methods, although our soft REST is still better than the previous method. Here are some more results. This is the input image. Second column is ground truth. Third column is the soft REST. And another two columns are our implicit field-based differentiable rendering results. We can see that with more flexibilities in the topologies, our reconstruction results much better than our soft REST. We can reconstruct objects with holes and with very detailed structures, and also with very diverse shapes of these objects. Okay, now let's talk about what shall we do for the 3D game character reconstructions. Okay, let me give the problem definitions. The input of our task, it is a set of the 2D drawings, like these ones. And the output is a 3D modeling. So the 3D model requires the geometry, means the mesh of the object, together with the appearance of the mesh. So the problem is very difficult. First, we can see that these 2D images, they are not consistent with each other. Unlike the real taken photos for the 3D objects that always satisfy the geometry constraint, 2D drawings are not always like that. And we only have a few hundreds of training samples. So the first step of our work is to perform pose and texture alignment. Because we can see that here are the 3D models. Here it is our 2D input for the front view. The pose, very different. And also the appearance also has some difference. So learning directly from here to here, it is almost impossible. Even we train a model, it is more like a noise. So we need to first align the pose and texture. How do we do that? So first, we find the camera pose and the bone adjustment to match the 3D and 2D for most of the parts, so that we change the 3D shapes and make it like the same pose with the 2D. And next, we use the differentiable renderings to deform the 3D mesh to match the 2D in details. So let's say this differentiable rendering deform operations, we call it operation O. Then we use a 2D image to replace the texture in the model to generate like this. And then we just perform the inverse operation of the O, so that the mesh together with the texture will change back to the original 3D model topologies. And finally, we adjust the bone to reach the reference pose, for example, the A pose. So now, by doing this step, we have matching examples from the 2D images and the 3D poses. And learning becomes possible. How do we perform the learning? So we just use the standard implicit field framework. So this is from our members' published papers in ECCV. So we can see that in the 3D space, we have different views. And in the 3D space, we have several sampling points. For each point and each view, we can find its corresponding matching point in the image. And we perform some neural networks, feature extractions, and we combine different views together to get the global feature. And finally, we have a classification network to classify this point as inside or outside. Here are some testing results. So it's still from the QQ speed. So here are 3 input images. So these are our reconstructed results. We can see that there are still some inaccurate predictions that may lead to some holes in the prediction model. So we need to fill these holes automatically. Here we use advancing from algorithms. So for the details of the algorithms, I'll skip here, but if you are interested, you can Google it online. So the basic idea, it is to find the angles between the holes, and we decide whether we should directly connect it or we use multiple points to connect it. After that, we perform further smoothing. We use Q-slim algorithm for mesh simplification, and we perform Laplacian smoothing. Now we can get very good meshes that fill in most of the holes and have very smooth results without losing the details, for example, like the fingers. With the mesh, how do we create the textures? So first, we perform the semi-automatic key points matching between the 2D different images. Then we perform the 2D image warpings to warp the 2D images into the 3D meshes. Then this still leads to some problems. So we perform a semi-automatic color filling for mismatching. And finally, we use the differentiable rendering to refine the final results so that its rendering results on the 3 views will match mostly to the 2D images. So here it is our final results. We can see that based on these reconstructed meshes, we can create a mesh with texture like this. That's all for my talk. Thank you for your attendance. If you have questions, please feel free to ask me. Thank you.